Okay, hello everyone. Welcome to another Wolfram Language Design Review for 14.3. I'm in a fairly random location today, so bizarre things may happen, but we'll do our best. Okay, so we are looking at discrete computation, and we'd got a certain distance last time in talking about find shortest curve and so on. Where are we starting now? Are we starting at Gaussian curvature or what?
Yes, Gaussian curvature.
Have we resolved everything? With
Um,
find shortest curve and so on?
yes, we did. And I think the main one was the renaming of geodesic curve to geodesic directional curve for the function repository.
Okay. Okay. All right. Now, what do I do here? I'm looking for.
So these are in the sources. The details are in the ref page.
I have no idea whether this machine has had its has updated the documentation. Does anybody have any idea?
I can ask.
Okay, so that would have been a good thing to know beforehand, but let's see whether I can do it here. So maybe you can start talking about what we're going to be looking at here.
That whole section here, including mesh processing and so on, it basically sort of utilities, computational geometry utilities. And yeah, so they're primarily sort of defined on meshes. You can define them on other things too, but what sort of ultimately works for complex regions and whatnot is meshes.
Okay. Somebody please get hold of Roger, the other Roger, to ask about this update, which is not working.
Yep.
Thank you. Okay, so I don't know what I'm going to be able to do here. And maybe it's better for you to share. Let's see what I can pull up here. So I don't think this is promising. This is not I don't think this is going to work. I don't know why, but it should work, but I don't think it's going to work.
Okay, I can go ahead and share.
So I mean, let's see if I could get anything here. No, it's just not there. So this is a fail. Okay, can you please start sharing? Charles, can you start sharing,
yes,
please?
so if you can
now.
stop sharing.
No, you start sharing first.
Oh, okay, so let's see, share. Okay. Okay, right. So let's see.
You're not sharing?
Yes.
Yeah, I'm sharing.
I don't see your share.
I do.
Oh, no, I do.
Guess there's a delay.
Okay, good.
Well, I should actually more start with the minimal curvature and the maximal curvature. Right.
Okay.
So the Gaussian curvature is essentially the product of the minimal curvature and the max curvature, and the mean curvature is the average of both. Right. So should just. So those are the key two functions. So we don't yet
show
have
examples, please. Can you show examples?
Right. Yep. So in this case of mass curvature of a sphere, I should radius R. So it's always
do the radius R. It's more interesting.
radius R. Oh, sorry. Yep. Put it at the right place. Is that right? And we can do pretty much the same for the mean curvature, 0, 0, radius R.
So the max curvature is the maximum in any direction at that point. Is that correct?
Yes.
Okay, so how do we get the curvature as a function of direction at that point?
We don't have that in terms of direction. Right?
That's kind of weird. I mean, we got to define some kind of tangent bundle at that point, right?
Yes, yes. Usually it's for manifolds, so it's defined at that point. Same as we had a discussion last time about the intrinsic and extrinsic coordinate and information, right? So this is kind of the intrinsic property for your space you actually get, right? So you can get it without having explicitly to define a tangent, right? Since is the smallest, the ball, which is tangent to that space, the radius of the ball, or 1 over the radius of that ball. So it's actually that value we are returning.
I'm sorry, but when we say max curvature, it's max with respect to different directions, correct?
Yes.
Okay, so we could imagine a function which doesn't necessarily define the coordinates, but it says what the distribution of curvatures is as a function of direction, correct?
Yes, possibly, yep.
And if we wanted to define a direction, we
How
could
would you give that? I mean, that's complicated.
Right, then you need to start to define the tangent and the property locally, and also it depends on how useful that will be.
I don't know, but presumably you can define, okay, what is the direction of maximum curvature? Is that a well-defined thing? That must be a well-defined thing. In the embedding space, there's certainly a direction of maximal curvature.
Yes, it's
right?
well defined, right? Yes, so it's well defined.
I
right?
mean,
Because
it could be. I mean, presumably it could be a whole minimizing set. You know, if it's flat, for instance, then you have the same curvature in many different directions, right?
Yes.
So the minute to max is like a whole set of such directions.
I mean, that's kind of like the gradient vector. We're trying to find the gradient on the surface. Right?
The gradient on the surface. You mean the normal? Or what are you talking about?
no, the gradient is on the tangent, right? That's what I mean.
Look, the curvature, there is a direction of maximal curvature, right? You're sitting at some point on the surface.
Mhm.
There is a direct.
You tuned out, Stephen. Hello?
There's a direction of maximal curvature, right? At a point on the surface, correct?
Yes.
You give the point, okay? So you have to find a direction. You can look all around, right? But what I was saying is that it may be flat, in which case there isn't a maximum. There's
I
like
understand. I
Okay.
understand. Well, there's a maximum value of the
Yes.
curvature,
absolutely.
but there's no meaningful maximal direction. Yes, I agree. Okay, but anyway, so we've got region max curvature at a point, but what about the region? What about the max curvature throughout the region? Is that something we define as well?
Who are the region? I'm not sure, because this is more a local property, right? The curvature.
Okay, but I mean, if I want to know for this whole region, we know what the whole region is, right? Because we got it. It's right there. It's a region object. We
Right.
can ask the question, what is the maximum curvature? And also the point of maximal curvature and so on. Am I right?
Yep, it's possible to, have all, request all those questions, yes.
What
But
do
we
we
don't-
think this is useful for? All this max curvature stuff, region max curvature. What do we think that's useful for?
So those are standard geometric property to actually characterize a set. Sorry.
Yeah, I understand. But why is it not relevant to see things like this whole to understand stuff about the tangent vectors at that point and so on?
I mean, possibly it's relevant, right? It depends on what you really want to apply. So if you really want to approximate your surface or study your surface at a point P, and you know the curvature, so you probably, if you are more thinking about the sphere, you probably know pretty much the spherical approximation at that point instead of working on the Euclidean, on the tangent space. So it depends on what you want to do.
Right, but so I mean, one example of what we could do there is, we say we actually give the approximating sphere, for example, at that point. Maybe that's a crazy idea. We give we know the at a given point on a surface, we can always ask.
But this is
if I'm not mistaken. Go ahead.
This is the inverse of that radius of that sphere, right? So the curvature is the inverse of the radius of that sphere, pretty much. So you can reconstruct that sphere from that information.
Okay. I'm sorry. Say that again.
So I said the result from the curvature is actually the inverse of the radius of the ball.
Yeah.
Right. So you can reconstruct the sphere from it, right? So that's why we don't have a specific function to give you that.
Okay, fair enough. Fair enough. But I mean, but isn't it in general an ellipsoid that is oriented in a certain direction? If the radii of curvature are not necessarily the same, right?
No, it's not.
No.
Wait a minute. Why are you talking about max curvature if it's a single, you're approximating the second derivative, right? The second derivative is a directional, there's different second derivative in different directions. So the approximation is not am I confused here? Help me out.
I think sort of it comes from curves, right? So for curves, you have this osculating circle, which is the circle.
And there's only a circle, right?
There's only a circle for a curve. Yeah.
Right.
Okay. So here we effectively want to do the same idea generalized to one dimension higher. This is only for surfaces in 3D, not for any other space at this point.
Yes, I understand.
Right? Okay. So now we can lay down a ball. We can actually lay down two balls of different potentially different radii, or circles for that matter, if you think of them as directional.
Yes.
Okay, and so we only characterize two, the extreme values, min and max, and then there's sort of combined measures of those, the mean and the product, which is the mean and the Gauss.
Yes.
That's it. That's usually, those are like standard properties that usually not nothing else. One could imagine.
But yeah, one could imagine other things, but we're not.
Yes.
We're not providing them.
Right.
Okay. I mean, fine.
I mean, we should do illustrations that really show what these things are. And if we'd had them, this review would have gone easier. As it will be for our users when they can see the illustrations.
Yeah. All right. Okay. All right.
Instead of inferring it from text.
All right. Okay. So it's just region point, and it gives a value.
Yes.
Yes.
I get it. Okay, onward to the next thing.
Okay. So after
What's region curvature function? Is that the one argument form?
Right, yeah. So it's the one argument from which return the region curvature function similar to the distance, where then you can do queries on several points.
What's that? Similar to the which?
Region distance function.
When you do region
Yes,
distance, you can get a
yes, I
function
know,
that
I
then
know.
gives, you know.
Yes, I know. Yeah,
Okay.
it sounds fine. Okay, next.
Next is the mesh processing. The first
So I think
function.
that let's start talking about the overall mission just a sec.
Okay.
Because that makes everything so much easier. So these are kind of almost like image processing functions. It's simplifying, which is lowering the polygon count but preserving the shape as much as possible. So you want to preserve
that's like resampling an image or something.
Yeah, roughly speaking. But this one has that additional thing that you want to not change the topology. You don't want to add holes or delete holes, that kind of thing. Refine mesh does the opposite. It's also resampling, but it ups it. It makes it finer, and also in additional, like for fem and so on, you don't want these like really skinny triangles, for instance. Those are bad quality triangles. So you try to up the quality of the mesh, basically.
Yep.
Smoothing. Sorry.
Yes, but I mean, one of the fundamental problems with these meshes is they're not 3D printable. For example, the meshes have enough weird imperfections and wrong surface normals and things like that they don't end up being 3D printable.
Yes, that's in repair mesh that deals with sort of that.
Okay.
But there can be problems with meshes even if there are correct topological, simplicial complexes and things like that. Like finite elements, if you give them then these skinny tetrahedra, it blows up. The conditioning is like super bad.
Yeah.
Smoothing is very much like low pass filtering, if you like, for images. And so that
will. I understand.
Okay, yeah. So just what it says: remove noise. Repair. We have had that before, but we've added more capabilities to it. So this is like a little toolbox of mesh processing functions.
Yes. Okay. But so, I'm sorry, how does this work? Criteria, second argument is the criteria. Okay. It's nice enough. I mean, presumably there are different things you're trying to achieve. They're different, in addition to those triangle counts and so on, there's like, make the mesh, how the mesh approximates, how the final mesh approximates the initial mesh has to be defined.
Right. I think that's what are the norms or the below max?
So those
normal deviation, max
quality,
normal.
Right. So this is more a geometric.
So Hausdorff distance, those
right,
last
but I mean,
two.
given that you say I want only 25 triangles to approximate this, there are many different 25 triangle approximations that you could give.
Yes.
Right. So
how do we determine which one we're giving?
It's not unique. It's based on the algorithm internally. So
no, but I understand. But there's only one criterion. We just have one built-in criterion. There's no method option or anything like that. Is that correct?
Yeah, there's no documented method option.
Okay, so fine. All right. So it is what it is. You get what you get.
Right.
Exactly.
Okay. Okay. Can you show me the pages can you show me smooth mesh, please? See some examples.
Right. So this is
okay. So is there a smoothing parameter?
No, there's no smoothing parameters. So
can I see the argument structure for this thing?
It's just one function, but it's driven by two method options, which are the standard one, where you use Laplacian or implicit Laplacian. So internally, roughly speaking, you average the point to smooth them. So in a discrete
I
form.
get it, but I mean the amount of smoothing depends on presumably.
I think
there's
that should probably gain more capabilities in the future.
Okay, fine. So there's probably some region, some smoothing radius, for example. Am I making sense?
Yeah.
Right. There is an infinite number of ways to smooth a region, right? So this one just use the standard way where you want to minimize the angle, right? Like I say here, you want to improve the minimum and maximal angle so you don't have extremely sharp corner and noise and the aspect ratio of those points. So the technique is, roughly speaking, doing an average. Maybe we have to write it explicitly, but it's pretty much in the discrete space, in the discrete mesh, you actually do an average of the point. Then
Yeah,
you
I
get that
understand.
smooth shape.
Right. And if you average it again, if you nest the smoothing, then you'll get larger and larger regions in the graph, larger and larger neighborhood balls in the graph being averaged out.
Right. And this
Although
is
I
the
have to
standard.
believe there's another parameter, which is when you take the Laplacian, isn't it like,
Yeah.
I don't know.
What order approximation? How far out do you go?
Yeah.
For instance. Yeah. I think that
Right.
this is as a whole universe of potential things.
Right.
Going.
But this is a good start.
Yeah.
Okay. Now, what happens if I say smooth mesh on like a polyhedron with, on a polyhedron specification?
Well, it should work on all mesh, right? So let's see what.
Or you might have to refine it first so you get enough points and stuff.
Sorry, say that again,
spiky.
please.
You might have to refine it first so you get more points, more polygons in it. I just want to.
Oh, wait. Oh, wait.
Bzz.
No, it's a bug we are fixing. Normally, we
Okay,
should
fine.
take
All right,
we
okay,
should
okay,
take
fine.
that for that
Yeah, okay.
that function. Oh, I should just.
Why don't we just pick one of our uniform polyhedra or something?
Oh,
Like,
right. Thank
they
you.
have
Forgot
names.
that. I never remember.
Icosahedron or something. Which
Oh,
has
right.
You can put spikes on it.
Well, it's failing on this version.
Okay, so it's just not working. Okay,
Right,
fine.
not
Keep
working.
going. All right. I get it. Okay, what's next?
And well, the next one is refine mesh. Right.
Show me an example.
So this is the
I see.
stand
Okay,
for Bonnie.
right. I understand. It's just filling it in a way that is, well, I actually don't know how it fills it in. I mean, we've got, presumably every triangle gets another point in the middle of that triangle to make a refined version of the triangle. Is that correct? Presumably with some,
yes, we adjust it and then you can actually see it from the set of point. Let's see.
But I mean, presumably there's some momentum, so to speak. It's not just you take the corners of the triangle and take the, and take the centroid or something and add that. You presumably have some kind of, there's some derivative coming in from the sides, correct?
Yes. And essentially also this one is driven by two method option, one which is adaptive and one which is uniform, depending on how far you want to adjust that.
Okay. Okay, sounds good. All right, let's look at repair, please.
Repair here is just the same function. We just improving the repairing of holes. So it's
which? I'm sorry, it's very hard to hear you. Say it again.
So in case where repair is just an update, repair mesh, where we are just improving the repair of holes. So when there are holes in the
but bottom line, is this actually going to work for 3D printing or not?
Not on this update. So we are working towards your machine learning a lot suggestion you are pushing. So, but not for this version.
All right. Okay. All right. Fine. Okay, let's move on. Subdivision surfaces.
Yeah. Roger, you want to give the intro?
Yeah. So these are really good for rich regions, kind of biological regions, let's say, and other things. And the way you specify them is with a mesh. And so I think you should show that mouse example that you have in a bigger worked example. Do you have that? Okay. This is an example we are developing for this release. Scroll down. So you start with a skeleton mouse. See the
Yep.
left?
I thought we were going to see an actual,
A real biological mouse.
yes, musculus or whatever it's called.
Right.
Yeah. Okay. All right. Fine. This kind of mouse. Yes.
That kind of mouse. But so in that sense, that's really the strength of these, and they were developed for character animation. So Pixar switched into these kinds of surfaces probably late 80s, early 90s, for their animations. And generally speaking, digital content creation for game characters and other things typically use these kinds of surfaces to create shapes. And so it's really a modeling play.
Good.
So if you want to go back to the core.
Hold on. Okay, yeah, let's go see how it works.
So the one argument form gives you the limiting surfaces, right?
So what it represents is that infinite limit. If you refine infinitely, it converges to an end surface. Obviously, for computation, we truncate that and we compute with a sort of a finite discretization.
Yes.
And the second argument, you can actually obtain the approximating mesh.
I get it.
Right.
Subdivision.
We generalize this, so it's sort of a subdivision for everything. Curves, areas, surfaces, volumes.
What happens if you do this on a polyhedron?
It should work.
Yes.
What is it? What is the limit of a polyhedron?
Here is a polygon.
Okay, polygon.
So down.
Okay.
Right.
Okay, here's
so
a
this
polyhedron.
is the spiky.
Okay. So it blobs out, but what's its limit? How blobby does it get? I don't understand what determines the scale size of the blobs. Do you understand my question?
Roughly speaking, I think you go sort of from, let's say if you have quads, they become, depends on which subdivision scheme, becomes 4 quads. So it halves every edge.
Yeah, but what's the limit? What's the limit of the spiky as I see? So if you just say subdivision region, it's going to be a sphere or what?
No, you see the limit. You can see the limit there.
Well, no, I want to see it. Just type it in as a limiting thing. Okay, explain why is this that?
So the limiting, as Roger said, right? So what we represent is up to a finite iteration where we detect that it converging to this shape, right? But behind the scene, we hold the object. So we don't have an explicit closed form of that limiting surface, but we can draw it and we can compute on it.
Yeah.
And you can set weights and whatnot for a subdivision scheme. So we have sort of named subdivision schemes now, but you could define your own in a way with your own weights. You have to kind of characterize that it's going to converge, not do two crazy things. So the famous ones that we have are go up. What a loop and what are the
and most of them are coming from
Kaplan-Clark loop.
Yeah, from spline, like cubic spline and such. So they're pretty much coming from an explicit representation for the limit surface. So the Kaplan-Clark, which is the classic one, there is the loop, which work more based on triangle, and the quad tree, which is a hybrid of the two methods. And we extended it to the case of curve 2D.
So wait a minute. So if I okay, so they're just okay, fine. So there are schemes for doing this.
Yeah.
The
So
subdivision.
a subdivision scheme basically says how you split it and what weights you use and stuff. And then you effectively run that to infinitely many steps.
Yeah.
Obviously we stop.
Right.
Yeah.
And let's see when this open. So this is kind of an animation of that process.
Yeah, okay, this is cool. All right, fine, great. So, I mean, like we can compute all this stuff like areas of a subdivision region, all these kinds of functions of subdivision regions. Is that true?
Yes.
Like
Like
cool.
2D and 3D.
That's very nice. It's very nice. Okay. Okay, what's next?
Well, so we also added function repository to actually, see the animation as well as working on the creation.
Okay, what's mesh edit?
Right.
Yeah,
you demo that.
So mesh edit, it's essentially if I manage to do that. So it's a lightweight editor, to actually allow you to, build that base mesh before you use it for subdivision region, right? So it's always hard to be, how can you actually start with a mesh before you apply your subdivisions? So what we build is a lightweight editor we will put in the function repository for the time being, which allow you to do that. So it's based on earlier work from Tim, he essentially used for his
illustrations.
So for example, you can take, in the family of the cuboid, you can actually, build such a cuboid and you can apply subdivision to it. Oh, no, sorry, that one. So you generate the subdivision to the object there. You can actually apply more and more. So you see kind of you are limiting surfaces. Or you can do all.
So what are the primitives that you can start from? You were just showing.
Oh, yes. So right now it's, family of cubes. So there is a whole family. Well, so this is.
So click one of those. Click one of those things. Click one of those.
Right.
Just click a picture. Okay. What is the status of text to 3D or various kinds of sort of sculpting things, AI-based sculpting tools?
Still at the exploration phase right now. So
for us or for 3D? The world?
Both. So we have been following that closely. So the world is still trying to do a pretty, something decent from text to 3D geometry, but it's not yet to the level of other technology yet.
Okay. But I mean, this mesh editor, this is a lot of work to build a whole mesh editor. And right now this is, the design here is obviously scratchy.
We want to put it in the function repository.
Okay, but what's it? Yeah, go ahead.
And as for all modeling, right, it depends on the type of, where you start and where you go. So this one is more, you start from an existing object and you apply a finite operation like you're in subdivisions, right?
I'm sorry, you start with this mesh editor, you're starting with an existing object. Is that what you're saying?
Yes, or from this base of object you have. So you're not starting from a point or empty cage and such. Or for example, this one doesn't have sculpting, right?
Okay, but what is the actual use case? What's the use case? Is it fixing things with 3D printing? Is it drawing diagrams? What's the use case?
The use case here is for subdivision, right? So is that how to build that initial mesh you feed in subdivision?
I don't understand. You've got a subdivision function. What do you need this for? What are you doing
to create the initial shape? Because you need an initial.
I thought you said you were getting the shape from somewhere else, and this is where it's an editor of existing shapes. What is it?
So take the example of the spiky. right?
Yes.
So you apply the subdivision, you actually get the shape, you get a shape.
Well, then you don't need the editor.
Yeah,
we
you
have
don't
the
need the
spike.
freaking editor. So
No,
what's the
but-
point?
But the point is that, maybe this shape, you want this to be more, you want a bump here. You want it to be
Okay, so
slightly
the
modified. So
editor, the use case you imagine is somebody is starting with an almost what they want 3D object, and then
Kind
they
of
are,
like a very crude form of it.
right. So
You
the
know,
example is
block model or something.
right.
yes, okay,
So like the example team use even to build this hand is, you can take this hand, put it in the editor, and maybe you want nails, right? So you have to modify a little bit the point and such, so that, when you smooth
okay.
it,
So
you actually get that shape.
you imagine that you're getting the base object model from somewhere else.
Yes.
Then the mesh editor is being used to make a tweak to it, and then the automated mesh smoothing algorithms are being used to clean it up. Is that right? Or is that not right? Let's
It's
get
right.
clarity about why we built this, because I'm surprised. It seems like a lot of work, which I never heard about, and I'm surprised. It doesn't seem obvious to me how it fits into the workflow.
So the workflow is the following. You have a base mesh, right? So, and the example is, is this hand, right? So you smooth it, you find out that, it doesn't look exactly what you want. Maybe you want this finger,
Yes, I
thumb
get
to be
it.
bigger.
Right. Yes.
So you get back to the editor, and then you move the geometry, right? So you move the thumb, maybe you move a point.
Okay.
If you modify the base geometry, the subdivision region change, right? Then you actually get the final shape you
we've
want.
got a whole family of editors. We've got ones for graphs. We've got ones for plots, which have never been very successful. But these are a lot of work.
We don't
What's
have
that?
one for plots.
Well, we absolutely do. We built it in version
Canvas.
3. I mean, no, you can click on a plot and you can start moving points around.
Yeah,
Nobody
but that's
ever
for
does.
graphics. No, but that's not for plots. That's like for graphics.
Yeah, okay, fine, whatever. But you can do it, and nobody does it, and nobody cares, right? So the question here is, for graphs, I know we want this for doing final tweaking. It's less obvious to me how important it is for final tweaking, other than for things like 3D printing repair for the 3D case. But maybe I'm wrong. But
Well, I think this is, as I said, the initial model that you give to this is a mesh. So how do you tweak that mesh?
Okay, I understand. If you want to do it interactively, but it's a lot of work to make a good mesh editor.
Exactly.
Right? This looks very scratchy.
Exactly. So we are not
It's not shipping with a
full
product.
No,
Right,
I understand.
and we don't want to pay, like you say, that cost of building a full mesh editor or competing with what's there. So what we are just building is a basic set of tools, and this is coming from something we already had in-house. We are improving to expose.
All right, okay. So it's just going in the function repository. It's intended primarily for do-it-yourself type use.
Yes.
Exactly. And if everybody
Okay,
loves
and we have no
then we can
current
invest.
plan to make this a mainstream, properly UX designed thing. Is that correct?
Correct.
No.
Yep.
Okay, fine. All right. But although I think first in line for doing that is a graph editor. Do you agree?
Yes, and we have been there several times, right?
I'm sorry?
And I say yes for the graph editor, and we brought design of the graph editor several times. We will try again.
Yes. Okay, fine.
Right.
Fine. But that's a serious thing that's going to involve UX. I don't know whether Tim is the right person, whether it has to be Noah. I don't know. But maybe we should have that as a separate discussion. I don't know if the graph editor is in the global project list. Can you make sure that it is? And if
It
you
is,
want...
it is, and we even have base already in the prototype build. Right?
Okay. All right. Okay, fine. Great. Okay. But I mean, what is the UX entanglement? Because there's going to be a whole bunch of UX work there.
For the graph editor?
Yes.
Yes. So, and this, right now the approach is first a lightweight version, right?
Which will be just in the function repository. Is that correct?
Yes. Or we...
No, it doesn't go into the product unless it's been properly designed.
Sure.
Okay.
We can discuss that later, and I can explain.
Well, it would be nice. It would be nice if we could get a lightweight thing properly designed, but let's not put something that is really kind of unusable because we've had that before. And guess what? People don't use it. And for example, in my case, where I've had many places where I would like to use it, I just gave up because it was not properly designed, didn't work properly. So, let's avoid that. Right?
Yes.
If we're going to put something in, then, I'd be thrilled if we can put something in, but let's not, let's make sure it goes through design and UX and so on properly. Does that make sense?
Yes, we will.
So, I mean, is that something for the next version? Is that something that we can realistically hope for or not?
We can have something for the next version. It depends on how far we want to go.
Okay, but so let's get it early in the designs, early in the, cycle. Let's look at that design and try and figure out how we can quarterize what has to be done.
Yep.
Does that make sense?
Yes, we will do that.
Okay, sounds good. Okay, what's next?
Right. So this subdivision, we already look at that. Next, visualization.
Okay.
Roger?
Let's take a look at region value plots. Please, can we go ahead and look at this? Thank you.
Yes.
Yeah, I'm not so sure about this at this point. It's
okay. So this is annotating a region with a function value.
Right.
Yeah. So, for instance, if you get those curvatures, how do you see them?
Right. Or if you just have a function, you want to,
No. Show me how you get the curvatures. Show me how you put the curvatures, because I mean, if there's a function that is defined for all XYZ space, right? Or all for full space, then this surface is just showing you kind of, this is essentially a texturing on the surface based on the function throughout space, correct?
Yes.
Correct.
I mean, it actually only computes on the surface.
On the surface.
Okay, but region.
I mean, Steven, you even asked that last time when we discussed, right? You want to plot a field on the surface on your mesh, right? So you define it on the torus, on the plot.
Right. With respect to the embedding space coordinates. It's not with respect to any intrinsic coordinates on the surface, for example.
No.
Correct. Yep.
I mean, on the other hand,
we don't use
you don't have to figure that out, right? Because we figure that out.
Yeah, no, I get it. But I mean,
okay,
so
but
in the
this
case
is
of
closely
parametric plot 3D,
so
hold on. In parametric plot 3D, there is actually a color function that you can give with respect to the parameters. You can either give with respect to the embedding space coordinates or with respect to the intrinsic parameters of the surface, correct?
Yes. But that's only for parametric stuff.
I understand, where there are parameters that define the surface.
Right.
Right. In the general case, you're saying you can only do it with respect to the coordinates of the embedded space.
Yeah, we don't know.
Okay.
So, but here's my slight issue, and I should have drilled into this. So this is very closely related to slice contour plot 3D. But maybe this works for, yeah.
Well, I kind of like this function. I mean, I think it seems useful. We've got geo region value plot,
right,
which I think works well.
Yeah.
And I mean, could you bring up the documentation of geo region value plot, please? Examples, please. Go to the examples.
It's just constant.
So that's a list version of this, basically.
I mean, it's just constant. I mean, it's literally constant on each.
Over each region.
Yeah.
But so now the question is, and I think we've discussed this, what happens if you want to plot, population density as a function of position, right? A function.
Mm-hmm.
See what I'm saying? And I mean, I think the syntax would probably allow that. You could have a function like an interpolating function of lat long as the first argument, maybe. Problem is, it doesn't define the bounds for that. So in both cases, do you see what I'm saying?
I'm not entirely sure.
Well, let me explain. So what you could imagine is georegion value plot of f of theta phi. Theta goes from this range to that, theta phi element of,
But that's more like a
something.
parametric plot then. I mean, the regions are so far beyond parametric stuff. I mean, just
No, Roger. Listen to what I'm saying. Okay. We've got the Earth. It happens to be parameterized by theta phi.
Okay, fine.
Right?
If we restrict it to the Earth, we have no problem.
Yes, that's what I'm saying. So the alternative, in the region value, in the georegion value plot, the only coordinates that we're dealing with are lat long.
Right.
Right. So we could imagine, and this is something for Jose, we could imagine this being, we've talked about, there's a whole bunch of stuff about georasters and so on. I think it will be useful to just make sure we are doing something with region value plot, which I generally like, but actually I'm now confused.
I mean,
what's the difference between region plot? I mean, there's a region plot, right? That we already have.
Right.
That plots. So what's the difference between region value plot and region plot?
Region just plots the region. There's no field in it. It's just the region.
I see.
There's no field. Same thing.
Well, then I think region value plot makes sense.
Yeah.
Then obviously it should be able to be, the second argument, the specification. Now, I mean, with that second argument, if we had something like an inequality defining the region in the second argument, what would that look like?
Implicit region.
Is that what we have to use?
Mm-hmm. You really want it equal to it? Oh.
I don't know why there's so much empty space there, but I mean, I like this function, region value plot. I don't see what is your concern about it?
Okay, it's primarily sort of a different interface to slice contour plot or slice density plot 3D.
But it's not just 3D. This will work in 2D, right? Region value plot will work just fine in 2D.
Yes, so there is that. I think it does, right, Charles?
Charles?
Yes.
Charles, are you with us?
Yes, can you hear me?
Yeah, now I can.
Oh, I don't know why it's delayed, but yes, it doesn't matter what behind the scene or what function is equivalent to, right? I mean, it does more processing on top than those functions, right?
Yeah. So it's an easy for certain things, it's definitely a more direct and easier interface.
Yeah. And myself, I didn't know that I can do that with the contour, slice contour plot until you pointed that out. So there's also that advantage. So and it's specific for regions.
Hi, sorry about that. Yes, please continue. Hello, can you hear me?
Yes. So
okay, can you please say something because otherwise I can't tell. I'm in a somewhat noisy environment.
There seems to be
can't tell.
There seems to be a delay by the time you get I say yes, and I'm opening the page, which is the next one, highlight region.
Okay.
And highlight region essentially highlight a part of a region. right? And it's quite useful, especially that we introduced the potential test curve, right, to highlight that subregion on such.
Well, so highlight region takes a region, a highlighted region, and a base region. Is that correct?
Yes. So that's yes.
Which is the order of arguments?
So
base
this
first.
is base first.
Base first, and then the highlight parts.
What to highlight and how and so on second.
And you, like you pointed out, maybe the name should be highlighted region instead of highlight region. That's also one thought here.
Well, I don't know. How does it relate to highlight graph? How does it relate to highlight graph?
Highlight graph is itself a graph, you know, with styling information. I think that this is what comes out here.
This is also a region, so it's the same principle, right?
Okay, so why wouldn't it be highlight region, just analogous to highlight graph?
Yeah.
The name is still fine. I just thought highlighted or highlight. Yes, fine.
But
because we tend to say, for example, transformed region, right? We emphasize the resulting object than the actual action.
Well, but
what is the resulting object? What is the resulting object here?
This is still the same object, but with a highlighted attribute.
How can what?
What's
the head of it? What's the head of it?
This is
okay. Well, what's the head of the thing that comes out?
A region.
Ah, I see. So this is where you store it. In region is where it stores a highlight.
It's in some metadata section of region. Is that correct?
Exactly. Yep.
Now
so
I understand.
You have additional object data store.
Okay. Okay. What can I see the stuff at the top, please? Okay, so the second argument there's a generic highlight, and then you can give style information just as you can for highlight graph, correct?
Yes.
Seems nice to me. Okay, should we go on?
Yes. The next one, AR publish, we just updated it to take molecule on more working on those cases on biomolecule.
Good.
So we think under correctly.
And it will take colors and things too, correct?
Yes, it's taking color. And we are fixing the cases where we are losing color, but you should render exactly the same.
Okay, cool. All right, next.
Next are the new color. Just double checking. Those are the ones
we went through these before, right?
Not with me, but with Tim. So we are just making sure that is those.
Yeah, I like them.
Okay, perfect.
They got some more zing. Okay, next.
Okay. Next, update for region dilation and erosion. So
to do 3D.
Yes, we can actually now take a mangle mesh and erode it.
Very nice. Are there any different parameters? It's still a one-dimensional thing to decide on the dilation, right? Dilation is still a one-dimensional operation.
Yes, you can take the ball, but you can also take any arbitrary region.
You can dilate with any region.
Any region.
If you just give a parameter, a real number, it's the radius of a ball.
Yep. And it's actually that case where we improve and we can do it in 3D, just the case of a ball, that one parameter.
I see. But wait a minute.
So that dilation is really like a Minkowski sum, is you just sum two regions. And so that second thing can be any region. It's very common and useful to do it with a ball or a disk in 2D.
I see. That's nice. Okay, but wait a minute. You said in 3D we're only supporting the scalar second argument. Correct?
No. This update actually just improved the scalar second argument.
The algorithm that we added this time around is specifically for the ball case.
No, I understand. That's what I just asked, and the answer to my question was yes. And so that I get it. Okay. And it produces some reasonable message in the case where you feed something, a cube or something in as the second argument.
Yes.
Please check. I mean, you don't have to do it right now.
When yes, I will check.
Okay. This is lovely. Okay, next.
Next, while we are working on the dark mode, is just an update that the attached cell of boundary mesh and such will be on dark mode.
Yep.
Next is the documentation. Roger, you want to go ahead and talk about it?
Yeah. So we have to refactor our guide pages every now and then when we grow functionality a lot.
Indeed.
Because we sort of outgrow the structure. And so Charles and me have been working on a new set of guide pages, and I think it's a great improvement. So it basically has two levels of presentation. The first top there is like a horizontal presentations, logical layer by layer. But then they're basically like verticals. So below that, we have a vertical set of things, two vertical set of things, academic first and sort of kind of industry second, if you like.
Geographic computation. You shouldn't call it geography computation at the very
You're
bottom.
right. Absolutely. And so I think
Computer
that this
graphics is a very weird term. I would avoid that term. I mean, I know what you can say, rendering, graphic rendering or something. I don't know what you want to call it, but that's too weird because that's too general a term. See what I'm saying?
Yes. Okay, for the time being.
Well, I don't think graphics rendering is quite right.
No,
but,
it's not right.
Yeah.
Put brackets around it. Put brackets around it so that you know you have to fix it.
Mhm.
Okay, can you scroll up, please? When you give a data structure, you should say data structure of KD tree. And I really absolutely would not put that first. Absolutely would not put that first. I wouldn't even line list that. I would put that as a thing where you can see data structure of blah. But I would it's absolutely not first. We don't want people doing that. That's some kind of codified, low-level thing. That's exactly what we're not supporting here. And where's Purist and things like that?
No. So in this vertical, in computational geometry, right, is more algorithmically driven, right? People want.
It should not be on the front guide page. Should not be on the front guide.
I mean, page. I think it's. I think that this is. I think it should be, but probably not KD tree. But computational geometry is very low level. Have you seen the textbooks in computational geometry?
Of course, I understand that. So maybe we can say data structure dash. And then the third line on there, data structure dash, KD tree, etc., and other data structures for computational geometry. You get what I'm saying? So we're not telling people you're using a library where you have to go and dive into this stuff, because most of the time for computational geometry, we're not. And you have a thing in your mind that this section is for experts, but people will just look at this page and they'll say, oh, it's a library where you use KD tree as a raw thing. See what I'm saying?
Yeah.
You can't assume that people know what's in your mind when you write these pages.
But we also need to send a signal that this is lower level. This is
fine, but you can use it at a lower level. So have a third line that says data structure, various data structures, blah, blah, blah.
Hmm.
Okay, can you scroll up again, please? Is find shortest curve really one of those things that we want to highlight on this page?
I don't think so.
Right. So it was new and shiny and cool, but I don't think it needs its whole line. I mean, also it explains very well. The name of it explains very well what it does. So, I mean, I like the direction this is going in, but it needs more work.
Yeah, I think it needs a few more rounds and then it'll be pretty good.
No, I agree. This looks nice. Looking at some more here. I mean, convex region Q, why are you explaining that? Why are you explaining that? I mean, it's an obvious what it is.
Okay. When I decide which function have to be on top here, it was based on the most common functionality people deal with. It's not based on my intuition or what we think is most important to people. Right? People are familiar to convex hole. That's the first thing you learn in geometry. Right? It's not the centroid or the end moment of geometry. So it's a choice, right?
Yeah, but convex region Q is a very obscure function used only by people writing. I mean, most convex hull would make sense there, but convex region Q, I don't understand why we put there. I don't understand why that testing function is an obscure thing used by people only writing code.
Okay, I mean, I won't argue about that, but this was in property and measure, right? So
yeah, I mean, click on that page, open it, because that has a long list of things in it.
Right,
I hate when people open us top. Irritating.
Okay, well, I mean, I don't think this is a great page. I think it should probably start, whatever. I mean, but that page is page is okay. But obviously we don't want to, when we're introducing geometric computation, it isn't the first thing you learn is how to write a slash semicolon condition when you define a function, right?
No.
Right, so it's just wrong. I mean, if you're talking about geometric computation, the thing you start with is regions and all of the general features of region. Why the hell is subdivision region above region? That doesn't make any sense. What's going on here?
As I say, it's a matter of perspective when you look at our region is a wrapper. Right?
Yeah, but it's the most important thing. It's the thing people use most of the time.
No, it's actually the opposite. We don't even generate it just in some cases. What you want is polygon, polyhedron, implicit region, mesh region.
All right.
Those are the object, right?
Well, I don't know. Yeah.
We're gonna write. This needs a few rounds.
Grind it some more.
Yes.
Yeah. Okay.
Okay. So, I mean, I think we'll need a
generally,
review.
The general thing is that there's sort of a yes, it's a rebalancing, right. And there's sort of the dual horizontal or logical layout of sort of a system.
Yeah, but
then sort of vertical to map to different.
Right. I am
groups.
highly supportive of rebalancing these things. Okay.
Yeah.
Just the thing to remember always is the thing that is in your head at the time when you write the thing about what the meta organization is will be utterly unknown and invisible to somebody who's reading the page. And these pages are intended for people who are skimming and scanning.
Yeah.
So it's important that they work in a skimming, scanning mode where people do not know your overall organization principle.
Yeah.
Is that fair?
Of course.
So, I mean, I think it's a very easy, when you're in the middle of writing one of these things, it's very easy for you to have some mental model that you are just sure is the obvious mental model, but it really isn't the obvious mental model when people just, scan it later. Anyway,
right.
Okay. All right. What's next? I think I'm really late for something else. Hold on one second.
Yes, we have another review meeting that's supposed to start.
Which is on?
Mathematical computation.
Okay, so let's try and wrap this in 5 minutes, and then I need to take a 5-minute break, and then we will start the next meeting.
Okay. So, next is the GPU array. So we are just updating and writing more example to show actually how.
Okay, all right. So there's no new functionality here.
Yeah, essentially. Yeah.
Okay, all right. Next.
Next
Hyperbolic, I was hoping to see, but it wasn't working last time I looked.
Well, it was working. So let me explain the idea, right? So essentially, the hyperbolic embedding we presented last time is actually the spring electrical embedding on the hyperbolic space, in this case, Poincaré, right? So, after the discussion, last review, we actually introduced the radial embedding, but on the hyperbolic space. For the time being, this is the syntax, which we definitely change. So the idea essentially is that for each of the layout we have, you can actually project or run it on the corresponding space, if it can be the hyperbolic space or a spherical space, like this. Right. So you will actually get the layout you were expecting.
Okay, but this is not a good way to do it. I mean, the first thing, the hyperbolic space, seems quite useless because hyperbolic space has to have a center, right?
Right, but in terms of the layout, you pick the layout on the center. Is that automation we are doing, right? And laying that.
But we have to say where the center is. So, graph layout, hyperbolic embedding, the spring electrical is just always going to make a mess, isn't it?
Well, yes. I
Okay,
mean, it's a
so-
layout, right? For a tree, will make a mess, obviously.
No, I understand, but it's since we don't know how to select the center in that case, it's like radial embedding, we know how we're finding the center somehow.
Yes. Even in this case, we can find the center. We know it's a standard technique. We know how to find the center. But the key thing here is essentially the idea, if is what we want to pursue, is that we have a base layout, right? Like in this case, radial embedding, right? We have a representation in the hyperbolic space, right? Or we have a representation in the sphere space. In this case, we can call it whatever name we want later on. So it's a matter of more to design what we want to follow, and if this is the type of layout you want.
Yeah, I think so. I mean, but then we should call that first one, we could call it hyperbolic embedding. That one there. That
Okay.
one. The one that is, because that's what people expect, isn't it?
Okay, yep. So we can do that.
I mean, or we could call it hyperbolic disk embedding, I suppose, if you think that's better. Is
Yes.
that more?
We were thinking that way, more aligned with the underlying embedding we are using in the Euclidean space.
Okay, so then we'd say hyperbolic disk embedding.
Okay.
Does that make sense?
Yes.
Yes. Yes. Right.
And now that first one, with the hyperbolic space and the spring electrical, I don't even know that that's worthwhile. I mean, is it ever going to give a good result?
Well, it depends on the graph, right? For trees, obviously not. But
give me an example of a graph where it could possibly give a good result.
Well, I don't know one on top of my head.
Okay, fine. I don't know of one either. So, I mean, we can try. I've got plenty of graphs that have lots of subdivision in them. We can try it on some of those. Why don't you go to the registry of notable universes, and you could easily run it on some of those graphs.
Yep.
See whether it produces anything reasonable. I'm deeply skeptical. I don't think it's going to work for anything. Whereas the hyperbolic disk one is absolutely going to work in a bunch of cases there. That makes sense?
Yes, we'll do that.
Okay. And the sphere, I'm not sure. I mean,
we have spherical embedding is actually the underlying thing too. It's the same idea.
Yeah, but so what is this different thing here?
So
when you say radial embedding sphere, what does it mean, and how does it relate to spherical embedding?
Exactly. So essentially behind the scene, even for the spherical embedding, right, is actually the spring embedding we are running on the sphere, right? We just call it that way. So this kind of expose the underlying structure, which is the embedding you do on the Euclidean space and the projection or the technique you use actually on the object.
Well, that's an interesting idea. And, perhaps in the future, we should think more carefully about, the analog of geoprojection and so on. In other words, the graph, what we're doing is in the typical case, the embedding space for the graph is a plane or three-dimensional Euclidean space, right?
Yes.
But you're saying that we're thinking of these as graphs in which the layout is done not in flat Euclidean space.
Yep, exactly.
Right?
Yes.
So I think that's an interesting idea. We should talk about that in more, because in general, you might say, I want to embed this graph on some weird surface, like those, subdivision region spikies or something. I can embed a graph on one of those in principle. I mean, are we in a position to do something like that, or is that far away technically?
Yes, essentially, if you have a manifold where you have the mapping, the exponential and the log mapping defined, so to the tangent space, we can do it. So
okay,
technically,
so that seems to me an interesting idea. So let's talk about that some more another time. To basically be able to give a region and then say, just like we have region value plot now, this would be kind of some kind of, and we have graph and graph 3D. We could say something like, I mean, I don't know how we call it, graph on a region type thing. Did you get what I'm saying?
Yep. Yes.
That seems useful.
Okay.
Okay, let's keep going.
So this is just that we added, I suppose, spring electric, option for those embedding, spherical embedding and gravity embedding. And in terms of usability for
Well,
graph,
I mean, we need to look at those more carefully. Not right now, but we need to look at those more carefully. I mean, that's fine. I'm glad we've added those options. Those will be useful. Have those options been appropriately added in the user assistance system and so on, so anybody can ever find them?
yeah, the documentation, we flag them and everything, yes.
Okay. All right. But I mean, I can imagine a situation in which you want to bring up an attached cell where those things are some kind of sliders or something, so you can actually see, for this graph, what happens if you change this or that. Do you see what I'm saying?
Yes, definitely, especially when we build the attached cell for graph, yes.
Right. Okay. Okay, cool. Okay.
And well, the last part is the computational. We just, some user request about the weighted adjacency graph for a default argument.
Okay.
Right. And some performance improvement for vertex delete and such. So
great.
That continuous improvement. And that's pretty much it. So number theory is just the book which is coming this summer, as well as a course. So that's it.
Great. Okay. Lots of good stuff. All right. I'll see you guys in a few minutes for the next meeting.
Thank you.
Okay.